All right, you guys, let's pick it up where we left off. I go back to my lecture document. Okay. We did A, B, and C. Let's get to D, E, and F. We're going to see some similarities, but definitely some differences. Let's jump on over. I'll switch cameras. Part D was the limit as x approaches -4. Our function was x squared minus 16 over x plus 4. Okay. So let's see. Let's think about that. Well, you know what? I mean, I bet you guys could probably just jump into this and tackle this one after seeing part C. Really very similar, different numbers and different function. I'll tell you what, go ahead and pause here. And if you feel comfortable, give it a try. Give yourself a minute or two. See if you can get the answer here to the limit of x squared minus 16 over x plus 4 as x approaches -4. So if you want to try it, pause now. Okay, I gave you a chance. I'm going to go ahead and do the problem. How would we go about this? Well, man, we say, okay, if I was to plug in -4, that would give me 16 minus 16, 0 over 0. So I know there's a hole. And if there's a hole, then my approach is going to be, okay, I'm going to try and simplify and then plug in. So I'm just going to kind of work right out here on the side, the limit. We're approaching -4. Well, this would factor as x plus 4 times x minus 4. Sorry, x plus 4 on the bottom. Okay, so these cancel out. If I just continue here, x minus 4. And now I can plug in -4 minus 4. Our answer to this one is -8. Very nice, very nice. Okay. You know, if you want to graph that, kind of confirm your answer. The idea here is that, you know, like we don't have access to a graph. I mean, I certainly would not know what that looks like. But you could graph this, you know, say at Desmos and then kind of confirm. But there you go. Cool. Part E. Now we're going to step it up. The limit, my M's get kind of sloppy. As x approaches, was it 3? Am I looking at the right thing? Yeah, okay, great. Limit as x approaches 3, square root x plus 1 minus 2 over x minus 3. All right, this is interesting. Let's see. What would happen if we try to plug in? Let's see here. Well, I can see I'm going to get 0 in the bottom. What would happen in the numerator? Three plus 1 minus 2, 3 minus 3. So that's going to be the square root of 4. 0 over 0, right? So, okay, with the square root, so we know there's a hole. Again, at x equals 3, all right, it happens to be, okay. So our same approach is going to hold here. We're going to try and simplify this. We're going to end up canceling the x minus 3, which will then allow us to plug in a second time to something simpler, get an answer. Like, but how are we going to simplify this? I mean, it's not going to be factoring, right? No. Totally different approach. Here's what we're going to do. This is something you you would have seen in algebra. It's a technique, but you probably wouldn't immediately guess it's what you're supposed to do here. What we're going to do is rationalize the numerator. Usually in algebra, we rationalize the denominator. That's not an issue here. Our square root's in the numerator. But it turns out rationalizing the numerator will do exactly what we want. How are we going to rationalize this numerator? Hey, if I was in a class, you know, and you guys have done the algebra review and that stuff, I'd probably like ask you like, hey, what should we do? And, you know, it might take some time before people kind of figured it out. We're not in a class, so I'm just going to tell you. We're going to multiply the top and the bottom by the same thing. We're going to multiply the top and bottom of this function by the conjugate of that numerator. So it's going to look like the square root of x plus 1 plus 2. That gets multiplied to the top and to the bottom, so we don't end up changing the function because we're essentially multiplying by 1, but it's going to allow us to, the way this is going to multiply out in the numerator is going to allow us to get that cancellation. It's pretty awesome. Multiply top and bottom by the conjugate. Here, it's of the numerator. Okay, so how's this going to work? Well, in the numerator, we'll need to FOIL. First times first. Well, hey, check it out. Square root x plus 1 times square root x plus 1 is simply x plus 1. Square roots, like, they end up squaring, right? Because it's multiplied by itself. Then we got the outside plus 2 times the square root of x plus 1 times the insides minus 2 times the square root of x plus 1. Oh, and the last, negative 2 times positive 2 is negative 4. We're going to simplify this, clean it up here in just a moment. The denominator, okay, we got to multiply those. Now you might think, well, we should FOIL there too. Don't do that. Just leave it in the factored form. Throw some parentheses around the x minus 3, the square root x plus 1 plus 2. Parentheses there. You don't want to FOIL. Why? Because in a moment, we're going to cancel out that factor, which is the goal. Okay. What from here? Let's clean this up. Hey, I notice these two middle terms cancel out. And then I can further simplify x plus 1 minus 4. And now we can see it. That's x minus 3. I'll just copy my factored denominator. Pretty slick. These cancel out. When they cancel, right, that leaves a 1 in the numerator. Algebra. Look at all this algebra happening, right? Multiplying by the conjugate. That's an algebra technique. Just the details of how that plays out, and then the canceling, right? Turns out here, the calculus is performing the limit. It's maybe it's like recognizing there's a hole. That's like part of the calculus. Okay, we actually did that in pre-calc, you know, at some point as well, you know, graphing rational functions and stuff, like where's the asymptotes and the holes and that sort of thing. So really, technically, the only purely calculus idea is here at the very end where we plug the 3. So we're good. We've avoided the 0 over 0 now. We can plug 3 in. That's going to be 1 over square root 3 plus 1 plus 2. And just clean that up. That's 2 plus our answer there. 2 plus 2 in the bottom is 1/4. We got it. We got it. So I won't do it here in the lecture, but you know, you might want to go back and graph this guy right there, that original function, square root x plus 1 minus 2 over x minus 3, graph that. And, you know, take a look at what's happening at x equals 3, and the function will have a hole at 1/4. Pretty cool. Okay. One other thing I want to mention here, when we whenever we learn a new concept in math, there will always be a new notation, a new way to write it. So when we're learning about limits, just one thing I want to point out, I didn't do that for the previous examples, but point out here, notice that like here, I'm just kind of exploring, fine. But when I start like going through the algebra, notice you always repeat the LIM x approaching 3. I'm always repeating that in every step until I actually plug the 3 in. At the moment I plug in 3, then I don't write that anymore, because now this is performing the limit. When I plug it in, now I've done the limit as x approaches 3, and it's just a matter of getting the final answer simplified. But until I plug it in, I keep writing it. Even here, when I kind of initially explored, I plugged it in and I did not write limit x arrow 3. Another approach, and students do different things, and there's multiple ways to do these with correct notation. Another approach would be, hey, I recognize I need to multiply by the conjugate, and almost like kind of doing that out on the side. And kind of all of this algebra sort of happens out here. And you kind of work through. So it's similar steps where you kind of work it, and then you say, okay, but once I've got it cleaned up, like in this form, now I need to go back and kind of stop doing work on the side and kind of go back and write the limit as x approaches 3, and that is equal to this, which is equal to this. So I could kind of like do, maybe all of, say, this work down here, kind of, without writing limit, maybe, kind of just doing that piece. But then, kind of do a lot. But then once I get to this, and it's all simplified, then I can't just immediately jump to that. We call it an abuse of notation. Then I need to come back and say, okay, the limit of this is equal to, and eventually 1/4. So there's some getting used to, and it might sound like I'm kind of nitpicking. Here's the thing. In math, correct notation is the equivalent of correct spelling and grammar and punctuation, say, when you're writing a paper. You probably, most of us wouldn't say like, oh, you're spelling these words incorrectly. Like, oh, you're nitpicking me. Like, no, like, we want to spell words and use correct punctuation and capitalize the correct letters. That's what correct notation is in math. And as we're learning, especially with limits, it takes some time, and it kind of takes some getting used to how to use correct notation. And that's like on top of the concept, right? So you're trying to just get the problem right. Like, can I just get to an answer that's correct? But there's another layer of, okay, once I am comfortable getting to an answer and it's correct, then I want to be sure that I'm using correct notation in that whole process of getting that answer correct. And both things are important. And I'll just tell you, kind of while you're learning this and on, maybe some of the early quizzes and stuff, incorrect notation, I'm going to point it out and comment on it, mention it, but you won't lose points for it. When we get a little bit further and we get to some later quizzes and certainly full tests, that's a different story. Like, you need to have correct notation even figured out at that point. Okay, that was part E. Let's move on. We've got one more here, part F. Now this one was very different. The sine of x over x. How are we going to approach this? Notice, hey, I try to plug in. And when I try to plug in, what happens? I get 0 over 0. The sine of 0 is 0. And then, of course, just that x. So I know I've got that whole. at x equals 0. There's a problem though. There's no way to simplify here. Right? Like even like there's no conjugate, there's no factoring. Like what are you going to do? We're going to go to our last resort. And this is even another technique. If all else fails, use a table of x values approaching x equals 0. What do I mean by a table? Well, here we're going to need actually two tables technically. We need one for the left side and one for the right side. Here's how it will look. We're going to have x and our function, kind of like x and y values. And similar over here. When you create a table, you want to use at least 3 x values for each the left and the right. Because we want to get a sense of how the function is changing as the x value is changing, like in that idea of the approaching. Okay. So notice that we are approaching x equals 0. If we approach 0 from the left, that means we're a little bit negative. So some good values would be negative 0.1, but then we're going to get closer to 0. How about negative 0.01 and negative 0.001? So we're starting off with, some x values kind of just a little bit to the left of 0, but then getting closer to 0. And this is really going to show us a good progression. I'm going to grab my calculator here. I'm going to say, okay, I'm just going to plug them in. Make sure you're in radians when you do this. So we got the sine of negative 0.1 divided by negative 0.1. Something kind of like that. 0.998334166. All right, I'm going to take that to 6 decimal places. I think that'll be good enough. 998334. Let's go with that. Okay, let's do it again. So that's kind of where we're beginning. All right, but just that one number doesn't tell us much. We need to see like a change, like a progression. So let's go with sine negative 0.01 divided by negative 0.01. Oh, interesting. 0.9999833. Okay. 6 places, 9999983. Be pretty good. And finally, sine negative 0.001 divided by negative 0.001. And now lots of 9s. It's kind of the same number above, but just stretching out a few more 9s. So if I go to 6 places, these are all going to be 9. Okay. So we can see how that's progressing. Let's do something similar on the right side of 0. Here we can take 0.1, 0.01, and 0.001. And I'll let you guys just kind of do this along with me in your calculator. It turns out you're going to get all the same values. I'm going to do it again just to be absolutely sure. 999983, yep. Turns out it's symmetrical. All 9s there. So we got 3. We could do more. We could like go 0.0001 if we wanted. I think this is pretty good. So what seems to be happening? And now we're just kind of doing this based off of, just the numbers that right in front of us, right? We don't have a graph. Let's see. Well, as we're getting closer to 0, what y value do we seem to be approaching from both directions? And it looks like these numbers are getting closer to +1. And that is the case on both sides. They're both headed towards 1. So there you go. Just kind of a last note. People kind of see the tables and they can, again, like, I think the word abuse is a good, like, they can abuse the tables and start using tables on everything. Let me repeat, tables are a last resort. You don't want to use tables when there's a better method. Turns out that with a table, we don't know with total certainty that this answer is correct. Now, it is correct in this case, and we're not going to try and like do anything really tricky in questions that we ask. And this is a, this is a good explorative kind of intuitive technique. But whenever a table is not needed, we definitely prefer to use that other technique. Why? When you think about this table, like, okay, so we're approaching 0. Well, how many more numbers are there between -0.001 and 0, or 0.001 and 0? Like, how much could happen between this number or this number and 0? Infinitely many things could happen, right? Just because that kind of feels like a number that's pretty close to 0 in our heads, there's still infinitely many more numbers between this number and 0. The function could do all kinds of wacky things, and we would never pick up on that. Now, of course, this one doesn't, and this progression is going to be fine for our purposes here. But what's the difference between that and, say, something like, if we go back to, say, part D here, we did a moment ago. When we did this and we canceled, we know, okay, there was a hole at x equals -4. And when we canceled, now there's no hole. Everything else is identical. We know for sure when we plug it into this and get -8, that was the answer to that limit. There's no question. It goes beyond just, well, if we plugged some numbers into a table, we could guess this. Like, no, this is, with this method, we know it without any doubt. Here, there actually is still some room for doubt, because who knows how close you have to be to actually approach 0. And we'd have to keep trying and trying forever, to be always kind of rechecking, well, what happens next, so yeah, just kind of leave you with, we're going to use this as a good technique, but it's not definitive. There you go. You know what? I'd kind of like to, let's graph that thing. Kind of clicking around here a little bit. Let's graph it just to be sure. The sine of x over x. It's kind of a cool, it's kind of got that sine wave, but it sort of like diminishes because you're dividing by the x value. So it makes it smaller as the further you get out. But right there at 0, notice, yep, it's honing in on 1. Now the point itself, if I can get it, there it is undefined. There's a hole there, but certainly that does approach 1 from both directions. Very cool, very cool. Okay. All right, you guys, let's stop this video here. See you in the next one.